Okay, so do you have any questions before we start? Now, if you remember the last thing we were discussing, in the last couple of weeks, we discussed the magnetic vector potential. We did some example calculations. We also discussed the magnetic scalar potential, which we can define only in regions which doesn't contain any current. And then on the last hour of Friday, we had started in the magnetic induction. And we had seen that in a general case, when we have a loop which might be changing in shape or moving around, and then we said that there is an EMF induced in this loop, which we could write in this form, d phi b by dt, where phi b is the total magnetic flux passing through our loop at a given time. And this was in the case when B was constant and the loop was changing its shape. Then we took one step more and said that this law would still be valid even if the magnetic field is changing, so that the B field, the B flux passing through our loop can change due to two reasons. Either B is changing or the area is changing or both of them. So this is not a derivation. It is just one step we took and which is verified by experiment. So that is something observational. We know that there's an EMF induced around any closed loop if there is the magnetic field change. Well, the EMF is, if the loop is not moving, loop is constant. So we say that if there is, for example, when the loop is moving, there is some work done on the charges in the wire which creates this EMF, but that is mainly due to the motion of the wire. So it is the motion of the wire that is doing the work, not the magnetic field. But if the wire is not moving, if there is no motion of the wire, then there is no such work done by the motion of the wire. And hence this work has to be done by some kind of an electric field created by the change in magnetic field. So in such a case, the EMF around the loop is nothing but the integral of the electric field around our loop, which we can also write as the integral of the curl of E on the area. In electrostatics, the curl of the electric field was 0, but now we see that if there's a change in the magnetic field, then the curl is not 0. Curl of E dot dA over a given. In fact, this is an arbitrary area, not necessarily one bounded by a wire. You don't need to have a wire. This is equal to minus d by dt B dot dA, which we can also write as minus. You see, in this example, in this case, we are assuming the wire is not changing. But since the wire is not changing, the area is not changing, that is, the area is independent of time. So the only reason why the flux changes in time is due to the B field. Since the boundaries of the area integral are independent of time, we can just move the time derivative inside. If the area is changing, we cannot move it inside. But since the area is constant, we can move the time derivative inside, but since B depends on both time and also position in general, it becomes a partial derivative. There is a 1 over C over here. And hence this equality should hold for any closed path or any area. So we have the integrand has to be equal. This is our first modification to the electrostatic law. In electrostatic, curl of E is equal to 0. In electrodynamics, curl of E is given by the time derivative of the magnetic field, magnetic induction field. In fact, this is why we have been calling B as our magnetic induction field, and H was our magnetic field. Now, any questions up to this point?
The area of loop is not changing, but it's also at the station.
What do you mean station? It's not moving. The area is not moving. It's not changing. There is no change on the wire. So that is why we say that the wire cannot be doing any work on the charges. Also note this minus sign. It is also called the Lenz rule, or the basis for Lenz rule, which basically states that the induced EMF is in the direction, the induced EMF or the induced current, if there is a wire, is in the direction which will oppose the change that creates it. Now let's do some examples and let's see what this means. Now the first example we considered was this system where we had a region of space which has a more or less uniform magnetic B field. And there was this conducting rod moving with some velocity v in this region. So as this rod is moving, what is the direction of the force acting on electrons? Upward or downward? Well, V cross B is upward, but the electrons have negative charge, so the electrons are pushed downward, which means the current will be moving upward. So this is the direction of the current. Now what will be the direction of the force? Well, this is a rod that carries the current, so now we can ask the question, what is the force acting on this rod due to the magnetic field, E field? What is the direction of the force acting on the wire itself? On the wire. No, the up and down is due to the electrons. The electrons are pushed downward. To the left. So dl is pointing upward in the direction of the current. dl cross B is towards the left. So this is the direction of the force acting on the wire. Now let's look at the Lenz rule. What does the Lenz rule tell us? So, okay, what is creating this current? So let's try to apply this Lenz rule. What is the cause of this current? So what magnetic field? Okay. So it is the motion of the rod, you are saying. That is creating the magnetic, okay? So the motion of the rod is creating the magnetic field. So the current should be such that it will oppose this motion. Now the current will feel a force which can oppose this motion. So the direction of the current should be such that the force due to this current will be in the opposite direction. And that is in the upward direction. So that's what we mean by the current will be such that it will oppose the change that is creating it. So as V is changing, what is happening to the magnetic flux passing through our loop? Does it increase, decrease? Let's say this is our Z direction. Is the flux positive or negative? Remember, flux, our definition of flux is the integral of B over our area. What is the direction of ds? Well, it is up to you, I mean, as you wish. What do you choose the direction of ds? into the screen. Okay, so you can choose it into the screen. So B dot ds, is it positive or negative? It's positive, so the flux is positive at a given instant, and the flux is B times A. With time, B doesn't change. What happens to area as the rod is moving? Area decreases. So the flux, it is positive, and its magnitude is decreasing. So the current should be such that it will try to increase the flux. So the reason why we have a current is the reduction of the flux passing through my circuit. So the current should be such that it should increase the flux. Well, the current is creating an additional B field. That is how it can increase the flux. So if I is in the clockwise sense, what is the direction of the B field that it creates? You see, now we have two kinds of B fields. One, the external B field, and once the current is running through our loop, there's the B field created by I. So the I should be such that the B field it creates in my area should be into the screen, so as to increase the B field. So that's also another way how we can determine that I should be in the clockwise sense. Because otherwise, if I was in the counterclockwise sense, the flux, the B field it creates would be in the opposite direction, and it would further reduce the flux passing through my loop against the Lenz's rule. Well, in a sense, the Lenz's rule is basically a statement of energy conservation. You see, for example, if you look at the F, if the force was in the direction of V, then as the rod is moving, it will accelerate on its own. So it shouldn't be. So, okay, the Lenz's rule is nice, but it's just a statement of energy conservation. If there is a change that's created a current, then that unless if energy is conserved, so the current should kind of resist it. So that we should do some more work to keep getting more and more current passing through our system. Let's assume we have a current carrying wire. It creates a B field. And let's just assume that the B field it creates is in the phi hat direction. This is my Z axis. Phi hat direction you can just determine by your right hand. It's in the phi hat direction, and it is given by B0 over B0 times L0, some length scale, over S sine omega t. Well, if we knew the current, then we would say that, okay, the B field will just go as 1 over 2 pi S, as 1 over S, basically. Well, but this is not a magnetostatic problem, so we don't really know whether we can use Faraday's law or not. So let's assume that the current is such that the B field as a function of time always has this form. And let's assume we have a rectangular loop over here. At t is equal to 0, what is the direction of the induced current? So let's start at t is equal to 0. Okay, B is 0, but nevertheless it is increasing in magnitude because of that sign. Now, what is the flux? Is the flux passing through our rectangle positive or negative? Let's start with that. Okay, to answer that question, first you need to choose a direction of ds. It's arbitrary, just choose whichever one you like. So which direction do you choose for your ds for our rectangle? Into the screen, okay. So is phi b positive or negative? It's positive. Is its magnitude increasing or decreasing at t equal to 0? Is it increasing or decreasing? Increasing. Increasing. At t is equal to 0. Let's see. B is increasing its magnitude. Phi b, since you have also chosen ds to be in the phi hat direction, it's just the product of the magnitudes. This is increasing with time. So the flux is increasing with time. So what will be the direction of the current? The current, according to Lenz's rule, it will try to reduce the flux passing through our loop. So what should be the direction of the current to reduce the flux? Just use your right hand. So the flux is increasing in this direction. It should be creating a flux, a B field in the opposite direction to balance that. So your fingers is just counterclockwise. So let's calculate at an arbitrary time the EMF. Or before that, let's do something else. Let's say this is our V. This is for V is equal to 0. Let's say this is our X, Y. V is equal to V0, Y hat. V0, positive constant. Direction of the induced current. At t is equal to 0. Or let's say not t is equal to 0. Now let me just put a Now the reason is that I want to take the limit omega goes to 0. So since omega goes to 0, this sine omega t over omega t is just 1. So B is constant. And Y is increasing. Now the loop is moving in the V plus Y direction. So what will be the direction of the induced current? So let's see. You already said that in this case, again, we can choose ds to be in the phi hat direction, so the flux is positive. Is it increasing or decreasing? It's decreasing. Magnitude is decreasing. Basically, it's going to moving towards regions in which B is negative, B is smaller. So the current should be such that it will increase the flux. So that is if the current is in clockwise direction. Now let's assume B is equal to phi hat B0, L0 over S. So let's assume V is equal to 0. In fact, we don't even need to assume V is equal to 0. EMF at T. What is the EMF of the loop, in the loop at the time t? It might be moving, it might be at rest, the current can be changing. This is what B is. This is our B field. The loop can also be moving.
What's S?
S is the distance from the wire. This is the B at the point R. And we are using cylindrical coordinates, so R is S, phi, and Z. Now, to calculate the EMF, remember EMF is always d phi B by dt. So we have to calculate the flux first. ds we had chosen, we can still use it, ds in the phi hat direction. So this is our rectangle. B is not a constant, so we have to integrate this B dot ds. We cannot just take B out of my integration. So for example, I can just assume we can even divide it into very small rectangles. Just take one of them. ds vector is nothing but ds times dz, because this length is our ds. Each one has a height dz. It's in the phi hat direction. So b dot ds just becomes b0 L0 over s times sine omega t over omega t times ds dz. Let's say this is the distance from the distance of the closest side is b. Let's say this length is a, this is h. That is equal to b0 L0 sine omega t over omega t. These are just constant in the sense that they are independent of s and z. dz, z goes from 0 to h, ds goes from b to b plus a over s. So this is equal to phi. The magnetic flux is b0 L0 sine omega t over omega t times h times logarithm of b plus a over b. EMF is nothing but minus d phi b by dt. So this is equal to minus b0 L0 h logarithm of b plus a over b times d by dt sine of omega t over omega t. No, this is not completely correct. You see, there are two things that can depend on time. One, that's sine omega t over omega t. The other one is b.
ds is b dot dt,
ds? No, not necessarily. I mean, I'm just, you see, the flux I am calculating at a given time. There is no dt in ds. But still, what are the quantities that are time dependent here are sine omega t over omega t, and also b is time dependent. So I have to take both of them into account. So the EMF will be minus b0 L0 h logarithm of b plus a over b d by dt of sine omega t over omega t minus b0 L0 h sine omega t over omega t d by dt of logarithm of 1 plus a over b. b0 L0 h logarithm of b plus a over b d by dt sine of omega t over omega t minus b0 L0 h sine of omega t over omega t d by dB logarithm of 1 plus a over b times dB by dt, but dB by dt is nothing but RB. So if you know the speed of the loop at an arbitrary time, you can calculate the total EMF. Now let's say that you found that EMF is positive. What is the direction of the current? So we have this loop. We found a positive EMF. What will be the direction of the current running in the loop? Clockwise. So because once you choose the ds, the direction of ds, you have also chosen the positive direction of the current. If EMF is positive, you will get a positive current running through the system, and the positive current, the direction of the positive current is given by, again, the right-hand rule. Just point your thumb in the direction of ds, and your fingers curl in the direction of the positive direction of the current. So that's clockwise. And if the EMF is negative, that means the induced current will be just counterclockwise. Now, any questions on this induced currents, induced electric field, how to determine the direction, both using the Lenz rule and using epsilon is equal to minus d phi b by dt? Lenz rule, most of the time it will be easier to determine the direction of the induced current using the Lenz rule. But even from this law, you can basically determine the direction of the induced current or the positive direction of the EMF. So you should be able to do both of them.
Is there 1 over C?
Yes, I always forget that 1 over C. Now let's look at electric generators. And electric motors. Well, they're basically the same thing. So what you do is, let's say you have you create a region where there is a magnetic field, there is a B field, and you can just put some rectangular, or in fact it can be any shape, it doesn't have to be rectangular, wire in it, and you send a current through it. Now, what is the direction of the magnetic dipole moment of this system? So the current is running in this sense around the loop. What is the direction of the magnetic dipole moment? Towards the left, towards the right. Left down, left up, right down, right up. How do you determine the direction of the magnetic dipole moment? No, the magnetic dipole moment is independent of the B field. Independent of the external B field. Of course, the magnetic dipole moment will create an additional B field, but in this case, this field lines that I'm showing are the external B field. So there is the magnetic dipole moment of the loop has nothing to do with that. So what's the direction of the magnetic dipole moment? Yeah, towards the left. Just use your right hand. I mean, whenever there is a direction involved in problems involving B field, use your right hand if you're not sure. So if you just curl your fingers in the direction of the current, your thumb points in the direction of the B field. Now here, this side is closer. So this is the direction of the magnetic dipole moment of this loop. Well, we know that there will be a torque acting on this due to this B field, and what's the direction of the torque? Remember, the torque acting on a B field is mu cross B. So it's outside. This is the direction of the torque. So which direction will it rotate? Clockwise or counterclockwise? Yeah, it will just rotate counterclockwise. So you start from this configuration. This is mu. It will rotate. Eventually, it will be aligned in this way. So it just rotated such that mu is aligned with the B field. Well, at this moment, there is no torque acting on the system, but nevertheless, the system has some rotational kinetic energy. It's rotated. It has some angular velocity. It cannot just stop there. So it will overshoot. So it will eventually to have such an orientation. It will eventually come to this orientation. If there are no frictions. So if there are no friction, the final angle that mu makes with the B will be equal to the initial angle that mu makes with B. Remember, the potential energy is equal to minus mu dot B. So the angle between the two will be equal when it stops. So at this instant, it's not rotating. But let's make a trick now. Flip the direction of the current. Most probably much before it stops. Let's say you just flip the direction of the current somehow. So what will be the direction of the magnetic dipole moment at that instant? So at this instant, let's say you flip the direction of the current. So how does the magnetic dipole moment is affected from this change in the direction of the current? So it will just change its direction, because basically the current changes its direction, and you know that the mu field you determine by just wrapping your fingers in the direction of the current. So if you change the direction of the current, the direction of mu will change. it will be now in this direction. So how will it rotate after this point? It will keep rotating in the same sense. So as long as you keep flipping the direction of the current, your wire will keep rotating. This is what we call an electric motor. The trick is how do you flip the direction of the current? That's something you have to work out. If you just open up an electric motor, did you open up an electric motor? A DC motor? No. It's either yes or no.
I don't remember.
Open one up. When you open them up, if you just pick up a cheap electric motor, what you will see is, well, there are these cylinders. On one side you have the rotating thing. Now when you open up, what you will see, okay, this is the cylinder, this is the external thing. So you will see, depending on the construct, there are magnets. Say this is the North Pole, this is the North and South Pole. So you have these magnets which create your B field. Inside you have some cylindrical object, and that cylindrical object is connected to this rotating rod, that is your axe. And inside you basically have again, it depends on how it is constructed. So these 4 pieces, some has 2, some has 4, some has more. And these pieces are held by some rods, some conducting, and they are there. You will see loops of wires running around them. So this is your wire that we have been discussing over here, but to create a large magnetic dipole moment, you basically have many turns. Each turn will contribute the same amount to this total magnetic dipole moment will be basically I times A times the number of turns. So the more number of turns you have, the larger magnetic dipole moment you get, and hence the larger torque, etc. And on one end of that rod you get these. Okay, so this is. Now these are just circular conducting sheets or metal pieces. Now the wires are connected to these metal pieces. And if you just look at from the side, this is your circular conductors, which are connected to your wire. Which is in the B field. Again, depending on how it's constructed, you can have some brushes. Let's say one metal piece over here. Another metal piece over here. And this thing is, as the motor is rotating, this thing is also rotating. Let's say this is connected to your battery, your AC or your DC source. So as that thing is rotating, after every half a turn, the direction of the current changes. So that is one way how you can obtain this flipping motion. Or if you want, you can just change it, depending on your design of the motor. You can, instead of 2, you can put 4 of them. So at every turn, it flips direction twice, not once. And this will basically give you a smoother running motor. You see, the torque is constantly changing. So in this example that we had discussed, you have some torque. It moves at a large angular velocity. Now, if you wait until your magnetic dipole moment is in this direction, then your motor starts, accelerates, it starts rotating faster, and then starts rotating slower and slower, then stops, and then starts rotating again, stops, starts rotating and stops. That's not what you would like to have. You would rather have a motor running at constant velocity, constant angular velocity, more or less. So to obtain that, what you do is, instead of 2, you get 4 or 6 of them, so that it will be flipping directions quite often. And at every turn, it will just keep rotating in the same direction. So the angular velocity, as a function of time, it won't be constant, but nevertheless, it will have such a shape. That's another alternative. You can just connect it to an AC motor, AC supply. But in that case, the thing you have to pay attention to is that, you see, there is a phase of AC, there is a phase of your rotation of your motor. They have to be in phase. AC will be changing its direction of the current at a fixed number of times. Your motor should be catching up. You have to make sure that it is catching up. If they go out of phase, you might end up your motor rotating in one sense at some time and then just flipping directions. It can be chaotic. Furthermore, you have to make sure that it is matching even if there is a load on the motor. That is, there might be some friction acting on your motor which slows it down, or some weight that the motor should lift. So it might slow down your motor, accelerate it, etc. Now, in this case, kind of the synchronization between the motion of the motor and the changes in the direction of the current is kind of done automatically. They are always in sync. If the motor doesn't rotate, then there's no flipping in the direction of the current. Let's look at the generators, and then we can go for a break. Well, the generators are basically, they have the same idea. It's the same construct. Now, what is the flux running through my system? Assume B is constant, uniform. What is the B field? Remember, it is B dot ds. B is constant, so I can just take it out. It is B0 times A times cosine of some angle. We can be more precise than that, but let's just call it theta. It's the angle between what you identified as mu and the B field. And then the EMF will be minus d phi B by dt times 1 over C, which will be minus 1 over C B0 times A times minus sine theta times d theta by dt. B0 A over C sine theta omega of t. Or if the loop is rotating at constant velocity, EMF is B0 A over C times omega sine of omega t. Now, of course, in the case of the motor, we send a current through the circuit, which creates the motor to rotate. Now, in this problem, in the generators, you just rotate the motor yourself. So if you rotate the motor yourself, what you will get is you will get a current from the motor. It's exactly the same system. Just in one of them, you send the current, cause some motion. In the generator case, you cause the motion. It can be, I don't know, by some hydroelectric plant. Due to falling water, you can generate this motion, or in in wind farms, it's the wind that is that's causing the rotors to rotate. And that motion is converted into current that we can use. And this is what we call an electric generator. It converts mechanical motion, mechanical energy into electric energy. Well, I mean, it depends on how fast you are rotating. What is the rotation frequency? In Turkey, it's 50 hertz, the standard. Like here, we get 50 hertz at 220 volts. Well, you see, this is, now what is theta? And phase difference between what? I mean, if you want to have a phase difference, you have to tell me at least two things which might differ in phase. So here we are only talking about the EMF. If you just use this current to run a circuit, if you use this EMF to run a circuit, in that case, there might be, depending on your circuit, there might be a phase difference between EMF and the current running in the circuit. But since there is nothing to compare it with, it doesn't just make sense to talk about phase difference. Now you can talk about the phase difference between the motion and the EMF. Now there's a phase difference between the flux and the EMF, if you want to say that. When the flux is maximum, the EMF is minimum. Because one is sine, the other one is cosine. There's a 90 degrees phase difference. Okay, let's give a 10 minutes break now, and we can continue after the break.